to the permanent magnet DC motors because they are most widely used, and you use them in the lab. One of the biggest challenge which people face is how do you go about selecting a motor? And we'll come to that in a little bit. But before we do that, we need to understand what exactly are the numbers in the spec sheet and how to make sense of them. So this is a derivation which tells you how to understand the working of a DC motor in an electrical and a mechanical point of view. So if you think of a motor, it will consist of a moving part. There will be some resistance because it's a wire, and then there's some inductance. Okay, because when you have a wire, it leads to a inductance, and that's this populate. So this whole thing is actually your motor. This is a motor, just modeled as 3 separate pieces. Okay, so R is the resistance, L is the inductance, omega is the speed, I is the current. There are 2 constants, and we'll talk about them in a bit. There's a electrical constant of the motor and there's a torque constant. If you open a spec sheet, you'll find them listed in the spec sheet. So the way we analyze this is we do a power balance. V is a voltage source. This is the power in. That goes to power a few things. It goes as dissipation in the resistor. It goes to power the inductance. So this is the voltage of an inductance times I, and then it goes to make the motor move. So that part is over here. Okay, so we can also do a torque balance. This is the mechanical part. This is the electrical part of the circuit. This is the mechanical part. Here, the torque produced by the shaft, so it goes in 2 parts. One is it goes to fight the friction. There's always some friction in the shaft, anything mechanical. And then there is the inertia of the shaft and the motor. Okay, so that's basically the torque balance. So these 2 equations, 1 and 2, comes from physics, right? Now this is a constitutive equation. What it means is that equation is specific for this motor. It comes from empirical relations, just like friction model is empirical, right? It's based on observations. So this is based on observations. When you try to plot the torque as a function of current, you see it's straight line. So the KT, which is a torque constant, comes over here. Now what we can do is we can sub in the value of, let's see, we can sub this torque in this equation. What we do is we'll assume that the inductance or the steady part is 0. The di dt is the change in current is 0 because we see that the current is more or less constant. So we can sub in the value of I, and of course the I is cancelled here. So when you sub it in, you get something which looks like this. So it tells you what, for a given voltage, what is the torque produced. And well, the speed is the two numbers here, right? Torque and speed, and you cannot independently control them. They're determined by, some of these are determined by the load which is there on the shaft of the motor. So with that equation, we can do some rearrangement. Here what I did was, instead of writing in terms of V, I wrote it in terms of torque. So just move the voltage on the other side. Now this expression is kind of powerful because now we can look at this expression and try to get the spec constant from the spec sheet. The spec sheet will give you a stall torque. Okay, it's the torque at which the speed is 0. So you simply put omega equals 0, and that gives you the stall torque. In the same expression, number 4, if you put omega equals omega max and t equals 0, the torque is 0, then that gives you the no load speed. Okay, so from this expression, put omega equals omega max torque 0. Okay, so this is something you'll see in the spec sheet, stall torque and the no load speed. So what you can do is, you can in fact simplify 4. Simplify 4. This is number 4, only in terms of stall torque and omega max. Okay. In fact, if you look at this, this actually is the equation. Is this equation? Omega max gives you a straight line which has intercepts of Ts on the y-axis and omega max on the x-axis. We are also interested in the power output of a motor. The power is torque times speed. So the torque, you can take this expression, put it in there, and then this is the expression for the power. Now, one interesting thing is to figure out what is the maximum power you can get from a given motor, right? Because when you try to shop for a motor, you might be tasked to find a motor which will provide a certain power. So here we're trying to understand what's the maximum power produced by the motor. So this is calculus. If you must have seen this before. What you do is you take the first derivative of power with respect to speed, set it to 0, and solve for omega. That gives you the extremum value. It may be power is maximized or power is minimized, but it happens when omega is half of omega max. In order to figure out if it is maximized or minimized, what you need to do is you need to take the second derivative of power with respect to speed. And it turns out that this derivative is less than 0, which means that when we set this to equal to 0, this gave us the maximum power. When the second derivative is less than 0, it means you are maximizing. And if the second derivative is greater than 0, you're minimizing. So this is maximizing. So then once we put in the value for this value in the power equation, we get P max is Ts omega max divided by 4. So to summarize, if you plot the torque speed curve, it looks like this, where Ts is the y-intercept, omega max is the x-intercept. If you look at the power, that is, just plot this equation as a function of omega, you'll see that power achieves a maximum value when the speed is half. Okay, and so that gives you useful information. That is, if you are shopping for a motor and you want a certain power, you can look at this curve to figure out if it will meet your specs or not. Normally, you would want it to be at a certain power at a certain speed. So if it doesn't fall over here, if your spec is right here, then you know that this motor will not fulfill those needs. And then you might have to shop for another motor, which probably does something like this. You'll shop for that motor. So that gives you a good idea. So, but all these things are possible from just two numbers: Ts, the stall torque, and omega max, the maximum speed or the no load speed. Okay, so this is a setup, a 20.25 HP DC geared motor. It's not shown here, but it's basically connected to the shaft. It's used to lift a mechanical load of 10 kg. So this is 10 kgs. Let's call that M. There's gravity. Weight 1. Using a pulley arrangement as shown, the no load motor speed is 300 RPM. So not no load speed, so it would be the omega max, 300 RPM. And the starting torque is 23.8. So the stall torque is 23.8. It's the maximum torque which the motor can provide. The frictional resistance is to neglecting inertia of the motor, the pulley, and the cable. We need to determine initial acceleration of the load, the steady state lifting speed of the load, and the output horsepower. So let's do it one at a time. Okay, so what's happening is that the motor has a stall torque of 23.8. So when you power this motor with that much torque, assuming that torque is big enough, then this load will start accelerating up, and we need to find that acceleration. So what is the acceleration produced by this starting torque? Because the initial acceleration. So for that, we somehow need to relate the stall torque with perhaps the tension in the wire. So what I'm going to do is draw the free body diagram of the mass. mg is down, and then it, in this case, accelerates up. And then we can draw a free body diagram of the pulley, torque. Okay, so there'll be some pin reaction at the pin joint, which we need to show. And then clearly there is a torque. Okay, this is the motor torque. Okay, so now what we can do is we can find the motor torque. It's going to be the starting torque, obviously, but because of friction, we can't get the complete torque. So TS minus TF. So then if you take moments, let's call this point O. If you take the moment about O, then we have the torque times the radius, I think it's 0.15, should be equal to the motor torque. And then if you do a force equilibrium for the mass in the vertical direction, we have T minus mg equals ma. Okay, so let's see. We have TS is known, TF is known, given here. T is unknown, T motor is unknown, A is unknown. So we have three equations, three unknowns, right? So you can solve for three equations, three unknowns. So I'll, in the interest of time, I'll not solve it, but I'll give you the final answer. So you can solve for all these three, T motor, and acceleration. Acceleration comes out to be so 4.73 meters per second square. Okay. Okay, next, the steady state lifting speed. So now the mass is accelerating up. Okay. At some point, what will happen is that it'll reach an equilibrium where the mass will not be accelerating, but move up with uniform speed. So that happens when when A is 0, mass is moving at steady speed. So in this case, remember we wrote T minus mg equals ma. Here acceleration is going to be 0 because it's not moving with it's not moving at any acceleration, moving at uniform speed. So we get T. We also wrote down torque of motor. See that expression. So we have T. We also have T motor is T times 0.15. Okay. And then we also wrote T motor is TS plus TF, rather minus, sorry. So what we can do is we can solve for TS. Remember, it's not the starting torque anymore, but it's the torque we need to move this up. So TS is T motor plus TF, but T motor is T times 0.15 plus TF, and T we know is mg. So mg 0.15 plus TF. So m is known, g is known, TF is known. TS comes out to be 16.7 Newton meter. So we've got the stall torque, and now we are asked to find the no load, I believe the no load speed, the steady state lifting speed. Okay, so we're going to exploit the fact that there's some torque, which is this. We know the no load torque, which is think it's 23.8. This is 23.8. You know the no load speed, this is 300 RPM. This point is given to us, and we need to figure this out. So it's basically a straight line. We need to figure out the speed at that. So here we have, we can write the equations of the motor. You can either look at the equations, but the equation is, if you remember, the equation of a straight line with intercept of 23.8 on the y-axis is going to be something like this. Omega divided by 300 equals 1. So that's the form for the equation with a y-intercept of 23.8 and x-intercept of 300. So all I do now is I put t equals 16.7, and omega is the unknown, equals 1, and then I can solve for omega. That comes out to be 89.5 RPM. And if you convert that to V, if you want to compute the speed of the motor, it's omega times R, it's 1.41 meters per second. Okay, and the last part, which I will leave it to you, is the power. It's torque times speed. The torque is 16.7. The speed is the one over here, 89.5. You need to convert that from RPM to revolutions per second, and then convert that to horsepower. So I have it in horsepower. It comes out to be 0.21 HP.